Welcome to today's webinar with the title Miniaturization for Industrial Electronics, Taking Cost and Reliability Aspects into Account. The speaker of today's webinar is Mr. Andreas Dreher from our Technical Project Management. And now I wish you lots of fun and new information.
Well, thank you, Andreas, for your kind introduction, and also welcome from my side. In our agenda today, which is now shown on the screen, it's live, we'll go under several points, and there are two main parts. In the first 3 points, I would like to get you an idea about the correlation between the miniaturization and the design rules and the impact later on the costs. And the second part is more reliability related, where we can show some results from some measurements. First of all, some remarks to my person. I've started 20 years ago in the plant in Schopfheim and worked in several areas like quality department and technical development. Some of my projects were qualification of new base material, introduction of reliability measurements, or the development of the ink technology for the PCB production. You can reach me under the shown telephone number or the email, or if you want to use the QR code shown next to my picture, you can create some bookmark in your address folder. So let's jump into detail. If you are related to designs of PCBs, there are a lot of different variables taking into account during the design phase. Just a few of them put randomly on the screen, and it's often very hard to find a start and the end point in these different variables. I like the picture of a gear system where you can see that all of these different points are interconnected to each other, and they are not independent. If you move on one little tooth gear, all the others will move with it. And so it's often it happens that you change a little parameter on one side and you get an output on the other side. The trick in PCB designs is to find a good correlation and a good output on the design settings. Let's go into details, and very often a good starting point is the components, because often the components define the functions of the final assembly, and there are a lot of different variables are depending on. And let's go in the first session into the effects on the cost side of the PCB. If we have a look on some different components on PCBs, then there are a lot of different types. Simple resistors or capacitors, MOSFET parts, QFP or BGA components. Let's start with a relatively simple one to get introduced to the idea of miniaturization and get on with a steep learning curve in the next slides. Let's choose a simple SSOP component with 24 connectors. And in this example, we have a pitch of 0.65 millimeters. The pitch defines the distance between the middle of one pad to the middle of the next pad. The pads in this example are so narrow that you cannot place through-hole components or through-hole drillings next to it, so you need a fan out to get more space for the necessary drill holes, as shown in this example. The pad sizes are 500 microns in diameter, and they are not fitting to the pitch of the component part. So we need a lot of space to do this fan out, which is lost for other components. A good example is to use microvias. Microvias are laser drilled holes just from typically one layer to the next layer. The diameter is smaller, maybe 150 microns. So also the land diameter of a pad can be smaller. In this case, the microvia pads are 300 microns, which is exactly the same size as the component soldering pad. So they fit directly into it. With this example, we can save some space on the board. And depending on the layout fan out, you see this example is maybe not the best option. There is some optimization possible. But with microvias in real designs, you can see that sometimes there's a factor of 4 possible of saving space, which is a very impressive benefit. Talking about space, this is often very quickly related to the PCB size. And maybe you know that if we produce your boards in our factory, we use pretty big production panels. The typical size is 24 times 18 inches, which results in a usable surface area of, for example, 418 millimeters times 570. Your board is then placed on this panel and stepped several times. And if the board size is not perfectly fitting into this panel, there is some space left, shown here in orange in this example. And this is unused space, which is lost, but the material is used. So at the end, you have to pay it, and the price for the single PCB will increase. If we can use such miniaturization shown in the last slide to save some space, and sometimes just a few millimeters of adjustment are necessary to fit in the same area as on the left side, you can include more PCBs, and so you get, in this example, a more output of 25% of PCBs, which is directly related in cost savings. Another big benefit on the use of microvias, for example, in combination of buried vias, which are mechanical drilled holes in the inner layers, is that you can use the space on top and bottom independent. With through-hole drillings, as the name implies, the hole goes through the whole board, and also on the bottom side, the space is blocked. You cannot place an additional component here. With microvias, you can use it independently and add more components on your board at the same space. So the SSOP components are maybe not the most complex parts. Typically, the complexest components on an assembly are BGA components. The BGA components have the solder points underneath it, and we see here a typical layout. I would show you an example where we go through the fan out necessary for a BGA with a conventional mechanical through-hole drilling. We have here 400 pads, and the solder pads have a pitch of 0.8 millimeters. And in this example, we exclude any any ground layers, sorry, any ground layers from it, and we just have a look on a signal layer. So let's start. As you see in the outer layer, a docked bone structure is used. So we have the green solder pads with the red dock bone pads for the through-hole drilling. And we use 0.5 millimeter pad sizes for the drill and 100 microns of line and spaces. So we can fan out 2 layers here on the outer layers. All the others are to be routed on the inner layers. If we have a look on the inner layer, we can see also here the pad size is 500 micron. Only one line is fitting through the inner layers, and also here only 2 rows are possible. If we go through all these layers, we see that only 1 row is possible to do with a fan out. So in total, we need 7 layers to fan out this component. And to be honest, a 20 by 20 row BGA is not the most complex in the world. So a lot of layers is necessary. And if you now take in account that you need additional ground layers, and you should always keep your stack up of a PCB symmetrical, we are ending here very fast with a pretty complex high layer multi-layer, which can get pretty expensive. On the other hand, if we have a look on the same component with a microvia fan out, what do you think how many layers are necessary here? We have similar pad sizes. The microvias are included directly into the solder pad. And also on the outer layers, it is very similar to the example before. Only 2 rows are possible to fan out. But on the next layer, we see very fast that we have here more space. The landing pad of the microvias are smaller. They have a 300 microns diameter, so we can fit now 2 traces between each pad and can fan out more rows on 1 layer. So in this example, on the 3rd layer, all pads can be fan outed. So you save a lot of additional layers, get the layer count down, get the board thickness down. Board thickness is also directly related to price. And also, this is a point for the later slide in the presentation, is a huge impact on the reliability. So it's always a good thing to have a thin board when compared to a thicker one. So I told you a lot of different values, and it's very hard to keep track all of them. So to have here some help for the designers, there are a lot of different design rules. Typically, one good starting point is the IPC standards, like some extracts here from the IPC 2221B, where you can see different requirements for the pad size. Some tips from my side. When you see the annular ring of landing pad, we always have process tolerances. And even with the most modern production equipment, there's still some tolerance inside the PCB construction. So keep your design rules as simple as possible and use the critical designs only for the critical components. If you have on the same board standard components, try to use standard tolerances here, which makes the production more easy, yields in a better yield, which in the end gets you also a better price for your product. Another point on the specification side, often the reliability of the boards is defined with the IPC class 3 level for the end properties. But on the other hand, sometimes the design is not fitting into this class 3 level. Also, the design has to fit in this level 3. For example, the smallest pad size for mechanical drilling is stated as 0.5 millimeters for conventional through holes. If you go smaller, like a BGA with a smaller pitch than 0.8, we have seen 0.8 is possible conventional way, but everything with a smaller pitch microvia is obligatory. It's not possible without it. Also here, the IPC standard is pretty thick, a lot of values. We have tried to simplify your work and created a design guide. It is available on our website since many years. It's updated several times. And here is a quick extract as a poster where you can find a lot of different standard values for a lot of different constructions. If you're going to use it, feel free to download it on our website, where you can see the link in the right-hand down corner. To give you some examples what you can find in this design rules, here is an example for a fan out of a 0.5 millimeter pitch BGA. As stated before, it's only possible with microvia construction. So you see different approaches. One is put the microvias directly into the pad. The benefit is you have larger solder pads, which is typically good for the reliability of the solder connections. Another variant is using dog bone structure. A lot of component data sheets use this as a standard fan out. One point here is you don't need the microvia filling to have completely flat microvias, which can save you some costs in the production of a PCB. Another variant, you cannot see it directly on this picture, is using microvias from 1 to 3. Main advantage here, you gain a different routing layer where you can create your fan out much simpler. Also, you find a lot of values, as mentioned before, standard parameters for the construction, or helpful tips if some special design considerations like very fine line structures, or that the copper thickness is process related, stopped at some level like 25 microns maximum on the outer layers. Talking about costs, I will show you on this slide a comparison of different HDI structures, what is possible and what is maybe the cost implication. Let's start with a pretty simple board. You can see here in this schematic, it's an 8-layer board. You can see in this layer that it has 1 microvia on top and 1 on bottom, 6 layers in the middle. And you can see in this arrow the indication that we have to go through one lamination process. And when I speak about lamination process, it includes also a complete run through the whole inner layer department. So the amounts of laminations gives us an indication on the number of process steps, which is typically related to more costs. On the next example, we see several different combinations which is possible on double lamination. So as mentioned before, in the design rule, it is possible to have microvias from layer 1 to 2 and also from layer 1 to 3. The stack up has to be fitted to this structure. Not all combinations are possible, but you create an additional routing layer, which can help definitely by the fan out. Another option is to use 2 different independent microvia layers. We have to go through an additional galvanic process for the inner layer, so the cost increase is shown here. and you can include also mechanical drilled buried vias on the inner layer and use this as a help for the fan out. But with a different drilling process, laser drilling is a different process than the conventional drilling. So it's an additional step here, which raises in a little bit more costs. We see the cost details later at the end in the summary. The most complex stacker possible in this combination is the use of two different microvia layers and the buried vias. They are all of your options for the fan out are possible, but it is also in this example the most cost-intensive process. If you need even more space for the fan out, you can go through a triple lamination. Then we build a simple 4-layer, drill it, fill later the hole, add in a sequential build-up, more microvias layers, and you have this construction as shown. If we compare now the price, it is very hard to say absolute price numbers because it's related to the amount of PCBs in the production panels, but you can here see an indication relative, starting with 100% for this simple single layer lamination board. We can see with more number of process steps, but the price increases, but with only 75% price increase, you can go to the highest, in this case, possible combination. To give you an indication, if we go for a simple 8-layer without HDI, we are talking about a price level of 90 to 95%. So we start for the using of laser drilled microvias is not so expensive. So I hope you've got an idea when we have different components that this influences the design rules, the PCB size, and for example, also the cost. If we go the other direction of our virtual gear system, we are coming to the area of reliability, and I will show you some impacts here also. First, let's get a common understanding what we are meaning here in this presentation about reliability. If you go for a full assembly, a lot of different influences are out there: soldering processes, components, environmental factors where you have temperature changes, humidity, different voltages. In our scope now is only the PCB, and we will show the influences on the several different via types. One important point is even flawless PCB boards will fail at some point if you go through harsh environments. A good example is here a simple piece of copper. If you bend it 100 times, it will bend fine. But if you keep on bending and bending, maybe after 1,000 bending cycles, it will break. And this picture is very similar on PCBs. You can go maybe once or twice through a reflow simulation, but if you overstress the board, it will fail at some times. The point of here is that the material will expand, and in the PCB production, we use different materials. So we have copper, Fe4, which have different values, which we will show later in more detail. I'm sorry, here slipped a German slide in it, but I will translate it for you as we go through it. We have some different literature where the reliability is discussed. And if we go on the right-hand side, most important factors which are influencing the reliability of through-hole components is the overall thickness of the board, the CTE expansion of the material, which we go in detail in the next slide, the drill diameter of the through hole. As thicker the drill diameter is, as more reliable it is typically, and the thickness of copper inside the hole. With the thickness of the copper inside, there is an optimum value. Here we have a comment that not always thicker copper is helpful. The typical values which everybody in the industry is using, between 20 microns and maybe 35 microns, is definitely the optimum. If you are way thicker than these values, you can see actually a decrease in quality, because the forces implied to the board are moving into the board. The copper in the hole is very very reliable, but the forces will move to other parts and will break the chain of reliability on the next step. For example, the inner layers will fail. So keep this in mind, but typically with this optimum value around 25 microns, you are pretty safe. So going into more detail, in this slide you can see a measurement of the thermal expansion of a TG135 base material. We have here the temperature up to 220 degrees, which is around the soldering temperature. And you see the expansion of a 1.6 millimeter thick board in microns. We start here at 50 degrees. When we heat it up, it will expand pretty slowly until we reach the TG value. And then the material softens and the expansion increases drastically, and we go on with CTE values up to 200 or 300 ppm per Kelvin. If we compare this to copper, copper has a value of 16 ppm per Kelvin. It is straight until it melts at more than 1000 degrees. So we see that the scissor between copper and material with higher temperature will open more and more. We get more stresses as hotter the boards gets. You can see it in real life boards when you do microsections, for example, after soldering. Here we have a microsection of a buried via, where you can see before it was flat. Through the expansion of the material, the annular ring was bent, which is indicating some stress. And as mentioned, as more often you bend it, it will more likely break. To compensate these points, you can use higher performing material, like material with TG150 or TG170. They have, on the one hand side, a higher TG value, so this bending will start later, and on the other hand, they are filled typically with some filler, which also reduces the coefficient of thermal expansion and help to get these forces down. If we compare now in this chart the reliability of different boards, what we've done here, we created a dedicated test with test coupons. We used 3 different boards. The layout itself is the same. We only changed, by modifying the stack up, the total thickness. So we are starting with 1.8 millimeters, another board 2 millimeters and 2.2 millimeters. And you can see in this chart here these cycles which are necessary to fail, to get a failed board. And here you see the statistical percentage when it fails. A good value to compare these charts is the scale. So the thick board with 2.2 millimeters will fail statistically after 60 cycles, which is shockingly low. You have to take into account that these tests were designed to fail. but they are real data. The 2mm boards fail at 86 cycles, and the 1.8mm board rely 180 cycles. So you can see even with small changes by 20% of reduction in the thickness can put up the reliability up to 3 times, which is a really big impact. If we go one step further and we include another board with a completely HDI stack up, the total thickness is 0.5 millimeters. The test causation conditions were the same. We included them to the test, and we have to stop the test after 1,500 cycles without failure. So you can see here the thickness of the board is a really big impact, and every little decrease of the thickness will help you here of improving your reliability. These tests were done with an interconnect stress test system. So we have these test machines dedicated for testing. You can use coupons put in the board, and they are heated up from room temperature to your test temperature. A typical value is 150 degrees, but even more is possible. And also a major influence is the reflow simulation. If you put the boards through several reflow simulations, like 6 times, you can see that these will really stress the boards. Afterwards, we can do microsection and statistical evaluations as shown in these slides, thermomechanical measurements to find your CTE value dedicated to your board and your stack up, and maybe get some design recommendations for improvement. If you are interested, we have these test systems in-house. We have in total 4 systems, and we are happy to create some tests in cooperation with you. Another investigation is test temperature. Again, we used conventional through-hole boards as shown before, and we have tested different test temperature. So we put them at a test temperature of 150 degrees shown in the black curve, and we got a statistical value of 1,500 cycles. By increasing with 20 degrees, the reliability goes down to 400 cycles, and at 190 degrees, actually the average failure was around 120 cycles, which is a very big impact and shows us keep away from these high temperatures. But again, checking with microvia constructions, we used similar test patterns and put it on the same test. We didn't find any failures at 170 nor 190 degrees, and even increased the test temperature up to 210 degrees. And still after 1,000 cycles, you can see the temperature change is a little bit increasing, but we didn't find a failure, which is defined by 5% resistance change. So also here we see a big improvement in the reliability by using a microvia stack up. Not everything in the real world which is shiny is gold. So it is also with stack ups on different microvias. There are some combinations which are not really recommended. A few years ago, the IPC announced that the directly stacked microvias on top of a buried vias is not recommended. This is also supported by some investigations by Würth Elektronik or the ZVEI working group of quality. What here can happen is through the material change. We have seen it before. the microvias are directly linked to the buried via, and the microvia will get the whole stress in this thick board, which can relate to cracks and so for failure of the boards. So there is a strong recommendation to change also existing designs and move from stacked microvias directly on top to staggered microvias with a space of 0.4 millimeters to the buried vias. And we are happy to help you in supporting you by changing your designs. Feel free to contact us. So this relates to a last summary here. I hope in this presentation I can give you a good imagination that all these variables and a lot more, not mentioned here, are related to each other. They are linked to each other. If I move one part, I can get an output on several indications, and a good planning here is necessary. So thank you for your attention. And if you have any questions, I will hand over to Andreas Schilp.